Let's do some A-level physics paper 2 derivations. Just a little disclaimer that these are not the only possible derivations, and there can always be a show question on multiple portions of the spec. Some derivations will be specific to some exam boards, so please use the chapters in which I will note which exam board the particular derivations apply to. Let's start off with resistance in series and parallel for OCR paper 2. So let's say that we have a total voltage V2, V1 and V2, resistance R1, R2, and total resistance in the circuit R total. Because V total will be given by V1 plus V2, this is Kirchhoff's second law, the sum of the EMFs is equal to the sum of the PDs in a closed loop. Then if we had a current I in the circuit, IR total will be IR1 plus IR2. These here will just cancel out, leaving us R total is R1 plus R2. On the other hand, if we had a parallel circuit, and let's say that the current here splits into I1 and I2, and let's say the PD was V, meaning that there's no internal resistance in the circuit, so it's V across all the branches. And also let's call this one R1 and R2. We can say that I total will be I1 plus I2, but I total is just V over R, so V over R total will be given by V over R1 plus V over R2. These here cancel out. 1 over R total is 1 over R1 plus 1 over R2. Next one is the wave equation derivation that V is equal to F lambda. Well, that comes from the fact that velocity is just distance over time. And we're going to set the distance to be equal to one wavelength and the time period to be equal to, or the time to be equal to one time period. Well, that just follows that V will be lambda over T times by 1 over T, which is lambda F as required. On to critical angle. Well, N1 sine theta 1 is equal to N2 sine theta 2. So theta 2 has to be equal to 90 degrees when theta 1 is the critical angle. Let's go at C. Then we get that N1 sine of the critical angle is equal to N2 sine of 90, which is just 1. Sine of the critical angle is N2 over N1. If N2 is equal to air, we get that sine of the critical angle is 1 over whatever the original refractive index was, N1. Let's have a circuit in which we have some total voltage and then two capacitors, let's say C1 and C2, with a voltage across them V1 and V2. Once again, we're just adding up the voltage, so V total will be given by V1 plus V2. However, Q is equal to CV, therefore V is Q over C. So we can plug this back into here, and then we get that Q over C total is Q over C1 plus Q over C2. Now this is essentially a series circuit, so the amount of charge can cancel out. 1 over C total is equal to 1 over C1 plus 1 over C2. Now, if we have capacitors in parallel, well, then it will be pretty similar. However, it will be the charge that is actually shared. So if we have some voltage Q total, Q1 and Q2 across here, then Q total will be Q1 plus Q2, but Q is equal to CV, so therefore we're going to have C total, V is equal to C1V plus C2V, but the voltage is the same across all those branches. So C total is C1 plus C2. Okay, next one, the capacitance of a sphere. So this is derived via the electric potential. So the electric potential at a distance r of the sphere will be given by Q over 4 pi epsilon naught multiplied by r. However, Q is equal to CV, meaning that C will just be Q over V. So this here will be Q, and V was Q over 4 pi epsilon naught R. Well, these are going to cancel. Then we get 1 over 1 over, which is just going to give me 4 pi epsilon naught R for the capacitance of a sphere. So it only depends on the radius. Technically, this is only in the OCR specification, but I'm pretty sure I have seen this in AQA questions as well. Next one, the potential difference across a charging capacitor. So imagine that we have this circuit. Let's say that we have some EMF V0. We also have a switch. We have a resistor VR, and we have a capacitor VC. Let's say that we close the switch. The voltage across the capacitor will increase, whereas the PD across the resistor will decrease exponentially. V0 is going to be VR plus VC by Kirchhoff's second law. The voltage across the resistor will decrease exponentially, i.e. V0 e to the minus T over RC, plus VC, which is the voltage across the capacitor. Let's rearrange for it. So VC will be given by V0, take away V0 e to the minus T over RC. VC will be V0, 1 minus e to the minus T over RC. The same equation also applies for the charge across capacitor. Q will be Q0, 1 minus e to the minus T over RC. Please note though that the current in this circuit will be decreasing with time. So I will be I0 e to the minus T over RC. It starts off at maximum, and then whenever the capacitor is charged, there won't be any current running through the circuit. I've seen this appear a couple of times in both AQA and OCR, and that is the half-life of a capacitor. So imagine that we have the exponential decay, so V is equal to V0 e to the minus T over RC, and a capacitor is discharging. Well, V over V0 will be e to the minus T over RC. So when we have that half-life, when T is equal to T half, V over V0, V over V0 is equal to a half. So a half will be e to the minus T half over RC. The half here is just a subscript, not an actual half. So let's take the ln of both sides, ln of this and ln of that. And then what we're going to get is ln of 1 over 2 is equal to minus T half over RC. The minus will flip the ln, so ln of 2 is equal to T half over RC. Let's carry on here. T half will be equal to ln of 2 multiplied by RC, and then ln of 2 is about 0.69. Multiply this by RC, which is the half-life of a capacitor. This next one is nice and simple, but if we start off with F is equal to Bill for a single charged particle, what we're going to get is that F will be B, the amount of charge per unit time multiplied by L. But then this quantity here, L over T, this here is just the speed. So the force on a charged particle will be BQ multiplied by the velocity V. If we have a charged particle which enters a magnetic field, then QVB is equal to MV squared over R. These cancel out, so R will just be mv over qb. If you're doing Edexcel because mv is momentum, then this here will be p over QB, but all of these are equivalent. Next one, we have a charged particle that is moving in a semicircular path in a cyclotron and magnetic field of flux density B and radius R. Show that the time period and hence the frequency do not depend on the radius. Okay, so we're going to start off with QVB is equal to mv squared over R, and we can also use omega squared multiplied by R and then omega being linked to the time period, but let's just do it using this equation. So we can cancel out the V's across here, and then what we're going to get is that V will be QB multiplied by R divided by M. Now, V is also distance over time because the speed is constant, and in this case, because it's a semicircular path, the distance traveled will be pi r, and let's say that this happens in a time t, which will be given by QBR over M. If this thing was moving in a full circle, which can also appear, there will be a factor of 2 in here, so just watch out for this. And notice how the r's just cancel on both sides. So I can just flip those, and I can go t over pi m over qb, and then all I need to do is just rearrange for it. So this here will be m multiplied by pi divided by qb, which does not depend on the radius. Additionally, we can also do 1 over the time period, which is equal to the frequency. Would that be QB over M pi, which also does not depend. Next one, we can derive E is equal to V over D from work done. Okay, well, remember, work done is equal to force times distance. E is equal to F over Q, the force per unit charge, and V is equal to the amount of work done per unit charge. Okay, so the force is just going to be the work done divided by the distance. So this here can go into here. So then we're going to have E is equal to W over D, and then we also have a factor of Q. But W over Q, this is just the good old voltage. So if we were to plug this into here, we get V over D. In other words, E is V over D. Sometimes we have both a magnetic force and an electric force acting on a particle, and they're equal to each other. And if that's the case, you get QVB is equal to E multiplied by Q. The charge cancel out, and we're left with that the velocity of the particle is just E over B, which is the ratio of the electric to the magnetic field. And by controlling those two, you can select the velocity of the particle. Next one, for nuclear, the density of the nucleus is independent of the nucleon number. So we're going to start off with density is equal to mass over volume. Now, the mass of the entire nucleus will be given by the nucleon number. Let's say that the nucleon number is just A, and let's multiply that by U. Divide that by the volume, which is the volume of a sphere, which is just going to be 4/3 pi r cubed. Now, in doing that, we have assumed that the mass of a proton is about equal to the mass of a neutron, which is about equal to the unified atomic mass unit. Remember though, now we have a formula for the radius of a nucleus, and that's about equal to r naught a to the power of a third. Let's plug this into here, and we're going to get that AU over 4/3 pi r cubed is going to give us r naught cubed. A to the third raised to the power of 3 just gives us a. Notice how the a's cancel, and hence density is independent and is just equal to this expression over here. Okay, the half-life derivation, we can use n is equal to n naught e to the minus lambda t. Well, n over n naught will be e to the minus lambda t. Then we're going to set n over n naught to be equal to a half. So 1 over 2 is e to the minus lambda t. Let's take the L1 of both sides is equal to minus lambda t. And then what I'm going to do is I'm going to flip the Ln. So Ln of 2 is lambda t. And now let's call this t half-life actually when this is equal to a half. So I'm going to put some halves here. I'm going to say that, let's just add this as an assumption here, that when n over n naught is equal to a half, t is t half-life. Okay, back to the derivation. All we need to do is just rearrange for t half-life, which is Ln of 2, divide that by lambda. Okay, next one, t squared is proportional to r cubed in gravity. Well, the way we derive this is by looking at the net gravitational force, which we can set that to be the centripetal force. So gmm over r squared is equal to m omega squared, multiply this by r. Okay, so let's cancel out these, and then what I'm going to say is that gm is equal to omega squared r cubed. Now, omega is 2 pi over t, so let's bring this into here. So gm will be 2 pi over t squared r cubed. Gm will be 4 pi squared over t squared r cubed. That means that t squared will be 4 pi squared over gm r cubed. Okay, escape velocity. So the total energy needs to be equal to 0. So the total energy is the kinetic energy. Let's call it EK plus GPE. Has to be equal to 0. In other words, a half mv squared minus gmm over r is equal to 0. This cancels out. A half v squared is gm over r. V is equal to a square root of 2gm over r. Okay, let's do the speed of a satellite. There's a couple of different equations. You can go, the gravitational force is gmm over r squared. Set that equal to mv squared over r for a circular orbit. And then we get that v squared is gm over r. In other words, v is equal to the square root of gm over r. If you're given just the radius and the time period, we can also say that v is distance over time. The distance is just the circumference, so it's going to be 2 pi r divided by the time period. And those two are equivalent depending on what you're given. The total energy of a satellite is equal to half of the potential energy. Well, how do we know this? Because a half mv squared plus, well, minus gmm over r. This here is just the potential energy, which is negative, and if we add them up, we get the total potential energy. V, we've just derived that to be square root of gm over r, so that means that v squared will be given by gm over r. We can just plug this into here. So we get a half m gm over r, take away gmm over r is equal to total. Okay, so this is minus gmm over r, take away half of it, so we're going to be left with minus gmm over 2r is equal to E total. And this over here is half the potential energy, which is equal to the total energy. Okay, this one here is for Eduqas and WJEC only. So how do we derive the critical density of the universe from conservation of energy? Well, we're going to have a look at the total energy, which is simply a half mv squared, which is the kinetic energy, plus the negative potential energy, which is GMM over R. Let's set that to be equal to 0, like so, for a static universe essentially. So then we get that a half V squared is equal to GM over R. Now one of the tricks here would be, I'll just do that here on the side, to consider that density is mass over volume, meaning that mass is density, multiply this by volume. So we can plug this into here, and let's also use the facts. Let's assume spherical symmetry and assume that the volume is equal to 4/3 pi r cubed. Okay, we can plug this into here, and then we're going to get a half V squared is G over R, and M is the critical density 4/3 pi r cubed. So this here is just density 4/3 pi r cubed. The critical density is when kinetic energy is equal to the magnitude of the potential energy. Now let's also say that V is equal to H naught, multiply this by R. So then we're going to get a half H naught squared R squared, which is going to give us G rho C 4/3 pi r squared. Those are going to cancel out. So H naught squared, what is that going to give me? It's going to give me 8 G rho C pi, then over 3. Finally, let's just rearrange for the critical density, which is going to be 3H naught squared over 8 pi G, which was what was required. One for Edexcel, but you need to be able to derive gravitational acceleration being GM over R squared. The way we derive this is by setting the net force, which is MA, to be the gravitational force, which is GMM over R squared. Those cancel out. A is GM over R squared, which is basically our gravitational acceleration. This one here is for Edexcel as well, and we need to show that the age of the universe is given by 1 over Hubble's constant. We're going to start off with the fact that speed is equal to Hubble's constant multiplied by distance. But additionally, speed is also distance over the amount of time. Then we just need to equate the two, and then we get that H naught multiplied by D is just given by distance over time. Now we can cancel out the distance, and what we get is that Hubble's constant is 1 over time, i.e. 1 over the age of the universe. The reason why we can apply this equation is because we are assuming linear expansion. And this question often asks about the assumptions as well. If you're doing Edexcel, the frequency of a mass spring system can be given by A is equal to, or can be found by, the defining equation of simple harmonic motion. Now this here is the acceleration. The net force acting on the spring is in the opposite direction to the displacement, and it's given by minus kx. Now because this here is the net force, we can say that mass times acceleration is minus kx. A will be minus k over m multiplied by x. Now if you compare those two, well, minus omega right over here, then this here will be equal to minus k over m. So this means that the angular velocity, omega squared, will be given by k over m. This here means that 2 pi over the time period squared is going to be given by k over m. So let's flip everything. T squared over 4 pi squared will be m over k, meaning that t squared will be 4 pi squared m over k. Let's carry on here. T will be 2 pi square root of m over k. Frequency will be 1 over that, 1 over 2 pi root of, k over m. And let's derive the pressure equation, which is one of the derivations that we need to know for the exam. Imagine that we have a box that has a side length L. This is actually a cube, so all the sides have the same length. Then the particle is rebounding elastically in an elastic collision with this wall. Well, if that's the case, it's going to rebound with a speed in the opposite direction. In other words, with a velocity of minus u. Let's say that the mass of the particle is just m. Well, if that's the case, the change of momentum is going to be delta p, which is equal to p2 minus p1. So this here will just be minus mu, which is minus 2mu. Now, what we ultimately want to do is work out the force on the actual particle, which is delta P over delta T. For that, we're going to need some sort of an estimate for delta T. The time between collisions provides us just with that. If the particle travels a total length 2L at a speed u, well, 2L over u, this here is just distance over speed, so this here is the time between collisions. Which also means that the number of collisions per second will just be the inverse of that, which is u over 2L. So delta t will just be the inverse of this, i.e. delta t will just be 2L over u. Our change of momentum was minus 2mu. Divide that by delta t, which is 2L over u, and this here, let's do some cancellations, giving us minus mu squared divided by L. Now, by Newton's third law, the force on the wall will be equal and opposite. In other words, F wall will be given by mu squared divided by L. So far, we have only considered one particle, but what if there are actually n particles all doing the same thing, colliding with the wall? Well, for n particles, the force will be a multiple of n. Next thing to consider is, well, what is pressure? Remember, pressure is just equal to the force on that particular wall divided by the area. The force on the wall is just mnu squared over L. Divide that by the area, which is just going to be L squared, because remember, the face is just L by L. In other words, we're going to get a factor of mnu squared, divide that by L cubed. But L cubed is actually just the volume of our cube. In other words, this here will just be equal to mnu squared divided by v. So far, we've only considered that the particle is moving in one direction, but if we're considering the RMS speed, we'll talk about this in more detail in a second, but CRMS squared, well, this here will just be equal to u squared plus v squared plus w squared, where these are the individual velocities in all three directions. And let's assume the particle is moving with roughly the same speed in each individual dimension. The assumptions in this derivation are equally important as the derivation itself. So CRMS squared will just be given by 3u squared. In other words, u squared will just be CRMS squared divided by 3. Let's take this and plug this into here to get mn multiplied by CRMS squared over 3v. Now, this whole thing was equal to the pressure. And my final step, and probably the longest derivation in A-level physics for AQA, would be to simply rearrange for PV. PV will then be equal to 1 over 3 mn CRMS squared. What assumption? Okay, Okay, so for Edexcel, we also need to be deriving this equation, 1/2 mc squared. This c, by the way, is the RMS speed, which is equal to 3/2 kT. Okay, now the way we derive this is via these two equations. PV is equal to 1/3 nmc squared, and also from PV is equal to nkt. So we can set both of these right-hand sides equal to one another because they're both equal to PV. So we can say 1/3 nmc squared is equal to nkt. The n's are going to cancel. So we get c squared, well, mc squared is equal to 3 kT. This here kind of looks like kinetic energy, so let's divide both sides by half. Actually, I'm just going to write divide both sides by half. So we're going to get 1/2 mc squared is equal to 3/2 kT. Now this video here was just a check, and it's just as important to practice problem solving, and this is precisely why you need to have a look at this video right over here and do an important question for practice.